Welcome back to Engineering Acoustics. Hi, this is Professor Ryan Harne. In this video, we'll learn how to tailor the signals to array transducers to exploit new wave propagation functionality.
So let's get started. So far, we've learned that acoustic arrays and the distribution of sources is a relatively simple means to beam acoustic energy using the array factor, whether that array is used for sensing, like a microphone array, or transduction and sound radiation, like for a loudspeaker array. It's really not difficult to tailor the signals provided to the array transducers either. So we could also digitally change the signals provided. So if we do this, what additional advantages can be created by tailoring the array signals? The first and foremost advantage is beam steering. It's the practice of providing phase delays to and from the transducer signals to change the angular direction of the major lobe. And considering our original line array, we see that we can apply these time delays, tau, or 2 tau, or 3 tau. The consequence of this is that for the ith element, we apply a time delay of I times tau seconds to the signal. So for the point source 0, there is no time delay. For the point source 1, there is a positive time delay of tau. For point source 2, we apply a time delay of 2 tau. And for point source -1, we apply a negative tau time delay. So we go from our original beam pattern for the line array to the case where now the acoustic pressure at the field point is equal to N times P naught of a slightly more complex ratio of sine of N 1/2 kd of sine theta minus sine theta naught divided by N sine of 1/2 kd sine theta minus sine theta naught. Theta naught is the angular tuning due to the phase delay, and it's computed according to C times the time delay tau divided by D, where T tau is the time delay. So what can we achieve with beam steering? Intuitively, time delays such as the example shown in the schematic of the top right, since point source -3 receives the signal first, its wave will propagate earlier than point source -2, and still earlier than point source -1, and so on. So it's intuitive to think that the primary beam of the array would literally be steered. Let's look closely at this. For an 11 source line array, when KD is equal to 3, and we apply variable steering. Now, when KD is equal to 3 and there is no steering, the primary major lobe occurs at broadside. But now, when we apply a steering of 30 degrees, our major lobe has shifted 30 degrees. This is quite predictable. But as the steering increases further and we go to a steering of 60 degrees, our major lobe becomes quite distorted. It's broadened. And our grading lobes have also increased in amplitude. And by this we mean, if we look at the side lobes for the case in blue, where there's no steering, some of the furthermost side lobes are about 10 decibels down. But as the array is steered, those same side lobes, if we look to the opposite side, they're probably only 5 or 6 decibels down from the major lobe level. So the grading lobes increase in magnitude. So while this is overall easy to implement, there are alternative effects that may counteract our original goal. At the same time, there are ways of managing this through array source placement or transducer placement as well. We can also focus using this concept of time delays. A focus is where the radiated waves converge. Or, if we are receiving waves, our reception sensitivity is amplified when the waves are originated at the focal point. Let's consider the following example. And in a similar way with beam steering, we apply time delays that correspond to the time differences required for the waves to propagate to the common focal point, or conversely, for waves to transmit from the focal point to the transducer. So by applying these representative time delays that you see here, we are able to counteract the fact that point sources 3 and -3 undertake longer travels for the waves from the point sources to the field point than the traveling distance from point source 2 and -2, which is still greater than point source 1 and -1, the distance between that source to the field point where we wish to focus. So the result is that the waves are transmitted earlier for point source 3 and -3 than they are for point source 2, than they are for point source 1, than they are for point 0 in the center. And what we see with the final wavefront, and especially when we mirror this effect, the waves show that they're beginning to converge in that wavefront along the center axis. And if we allow the waves to propagate one further wavefront, we see that they do highly converge near that focal point that was geometrically selected. We can additionally shade arrays. No longer do we manipulate the phases or time delays, but now we manipulate the amplitudes. So in other words, we might send the central transducer a larger amplitude than the transducers 1 and -1, then 2 and -2. And the result of this is that we use some sort of shading routine to lead to the different type of array factor we're interested in. Binomial shading is one common way. It specifically suppresses side lobes. We use Pascal's triangle to use binomial shading. In other words, if we take an example of n sources in the array, where n is 6, we apply the binomial shades of a magnitude 1 and 1 to the two central transducers, of 1/2 and 1/2, or 5 on 10 and 5 on 10, for the next adjacent transducers, and then we apply 1 on 10 and 1 on 10 for the most distant transducers from the array center. What does this beam factor look like for a shaded array by binomial shading? If we consider the case when n is 10, we have 5 transducers along each side of the array center. What we find is that when the weights are taken to apply to our sum of acoustic pressures, we then take the absolute value of this quantity to determine the array factor. And the result is that the side lobes are completely suppressed. We see this in the red curve when compared to the blue curve that is the array without shading. Now, on the other hand, the major lobe is broader with shading than without. At the same time, we have successfully suppressed the side lobes, which is a pretty significant achievement given that we are operating the array at a very high factor of k multiplied by d. This principle can be taken much further. When we have arrays of directional sources, we can achieve some very unique functions. For instance, we might array an array in different axes, and this occurs quite regularly with loudspeaker arrays. So we have a single line array here for loudspeakers, and then it's arrayed in another dimension. Same thing occurs with microphone arrays. This array with non-uniform microphone spacing is repeated 5 times around a circle. Microphone arrays are often rotationally symmetric. We can have arrays of directional loudspeakers and many other examples. So what is the total beam pattern? Well, it's the product of the array factors. In other words, we take the beam pattern for one array and then multiply it by the beam pattern due to the other array axis. So in the case of the loudspeakers, we would determine h of s, theta, and phi for this loudspeaker array. And then, given the array in the other dimension, this would be our array factor, h of a. of theta and phi. And the product of these two array factors is the total beam pattern. And this principle is called the product theorem. This makes it very convenient to calculate the beam pattern for multidimensional arrays, especially rotationally symmetric arrays, for which it's not immediately apparent how to take all of the transducers at the outset and determine a total beam pattern. So let's summarize what we've learned. We've learned that acoustic arrays are widely used for source localization, sound reproduction, sound virtualization, and more. And it's due to the fact that there are multiple capabilities in acoustic arrays that are unachievable by individual sources alone. For instance, we can beam steer. It gives us the means of angularly steering the major lobe of an array, and it's often employed digitally and in real time. And exposure to and understanding these advanced acoustic signal processing techniques helps us to understand and engage in acoustic array processing and analysis in practice.
That's it for this video. In the next video, we'll gain more intuition regarding acoustic wave focusing.